last lecture we saw that a map such as the logistic map, when you vary the parameter, the period 1 fixed point, it changes its location as well as its stability, and at the value r is equal to 3, the period 1 point becomes unstable, a period 2 orbit is born at the so called period doubling bifurcation. Now, how does this map actually change? As you increase r from, let us say, 1.8 to 3, notice that the point at which it crosses the diagonal, namely the fixed point, that keeps changing in location along the map. The local stability, which is given by the slope of the map, the derivative of the map at this fixed point is 2 minus r, and so when r is 1.8, it is actually small and positive. When r is equal to 2, it is equal to 0. When r is 2.7, it is 0.7 negative, and when r is equal to 3, it is negative 1. So, the orbit itself is born at r is equal to 1, and the stability, that is the value of f prime, or this derivative over here, that keeps decreasing. So, the orbit, in a sense, the fixed point is becoming more and more stable. When r is equal to 2, the slope is equal to 0, and this is the most stable that it could possibly be. So, such behavior is called superstability, namely to have a slope 0, because this means that that fixed point attracts everything maximally. When you take the, so to just come back over here, at this point you have the period doubling bifurcation. The period 1 orbit is no longer stable, and instead a period 2 orbit is born. Now, if you look at the doubled map f2 of x, and as we have discussed in earlier lectures, looking at the intersections of the map with the diagonal tells you the fixed points. So, here are the two fixed points of period 2, but if you look at the doubled map, let us say at a value r is equal to 3.4, notice that the inner part of the map, if you were to just concentrate on that particular part of the map, expand it and flip it around, then when you flip it around and expand it to the required scale, you notice that it looks a lot like the map f of x at another value of r. So, namely that if you try to look for some point in r where the intersection is on this side, so this is where that intersection looks to be located. Notice that it is over here. So, when you look at the map, turn it around, expand it, it looks like the same map at another value of r. Now, as you keep changing the parameter, the stability of the fixed points change. Recall that if x1 and x2 are the 2 points of the period 2 orbit, then the stability of the orbit is determined by this quantity f2 dash or f2 prime, which is the derivative of the map at the first point x1 times the derivative of the map at the second point x2. And the periodic orbit is, of course, it's stable if the modulus of f2 prime is less than or equal to 1. Now, these 2 points of intersection of the period 2 orbit, here and here at one value of r, as you keep changing r, those points migrate, and now these 2 points are over here and over here. And as you can see, the slopes keep changing. They are born, both slopes are 1 in modulus, and then they slowly keep changing, and the product over here can first decreases to 0 and then it increases, and therefore one can expect that in the same way as period 1 bifurcated to period 2 orbit, period 2 itself at some point will become unstable and it will give birth to a period 4 orbit as r is increased. This is really the heart of the period doubling route to infinitely long periods. Period m 2 to the m orbit becomes stable at r sub m. When period 2 to the m becomes stable, the period 2 to the m minus 1 necessarily becomes unstable, and so period 1 became unstable, 2 was stable, 2 becomes unstable, 4 is stable, 4 becomes unstable, 8 is stable, and so on and so forth. The values of these bifurcation points, of the parameter at these bifurcation points, is as follows. R0, namely where period 1 becomes stable, is 1. Period 2 became stable at 3. Period 4 becomes stable at 3.449. Period 8 becomes stable at 3.544, etc. Period 16 at 3.56, and so on. These are known to much higher precision. Some of them are even known analytically. But as you can see, the difference between the between successive members of this sequence, namely the width of the windows of stability, so to speak, those are decreasing. This was investigated extensively by Feigenbaum in 1978 and earlier, and he defined this particular ratio, the ratio of the widths of these windows. So, what is the width of this window divided by, so here is the window where period 2 to the m is stable, and this is the window where 2 to the m minus 1 is stable. So, these windows keep shrinking. I think there should be this is 1 over delta m over here is defined. Okay. So, Feigenbaum noticed that these windows, not only do they keep shrinking, but they do so at a geometric rate, and they do so with a very interesting set of properties. The first property is that this ratio decreases approximately by a factor of 5 at each step, and as m goes to infinity, this reaches the value delta, which is this number 4.669. This is an irrational number, and it's known to many more places of decimal. All these period doubling bifurcations, they accumulate at a value of r infinity, which for the logistic map is 3.5699, etc., etc. So, at between 3 where the first period doubling bifurcation takes place, and 3.5699, which is somewhere over there, all period 2 and all powers of 2 have occurred at that point, because each of these windows is shrinking by a factor of about 5. The rate of convergence of this quantity is geometric. This number is very particular to the logistic map, but it turns out that this number delta over here is not, and this is a universal number. It was the first of the universal numbers that was discovered by Feigenbaum, and it is an extremely important number, because the way in which this period doubling cascade, the widths of the intervals in which these are stable, each particular periodic orbit, that shrinks at this particular rate, 4.669. Now, coming back to the doubling, you note that we observe that the middle part of f2 of x at some value of the parameter. When you flipped it and you expanded it, it looked like the map itself for another value of the parameter. This led Feigenbaum and collaborators to look at the following composition. This doubled function looks like itself when it's rescaled. So, Feigenbaum and Cvitanovich wrote down this particular equation which describes this doubling operation. So, if you have a function which when rescaled by a factor of alpha, doubled, flipped around, then it looks like itself. So, if you can find a fixed point of this equation, or namely if you find a function which satisfies this property, then you will begin to understand what happens in this particular map. And you solve this equation for some polynomial smooth function of g. There is a sort of an involved way of doing this, which is described in a series of very nice papers by Feigenbaum. You find that alpha is a number 2.503 or thereabouts, and this is again a universal number which is true for all quadratic maps. So, requiring the doubled function to look like itself and asking for this function g of x to be of a polynomial type, that gives you this universal number 2.503, and along with delta, which is 4.669, these two numbers quantitatively characterize the qualitative statement of a period doubling root to chaos for quadratic maps. Okay. Let me just state this again because this is sufficiently important. To say that you reach an infinitely long period by doubling at discrete values of the parameter, so period 1 gives rise to period 2 becomes unstable, gives rise to period 4, and so on and so on and so on, that is a purely qualitative statement. What Feigenbaum did was to say that not only does this happen as the phenomenon, but the value of the parameter at which this happens, these values keep shrinking at a precise rate, which is 4.669. And there is another geometric characterizer which tells you how you must rescale the function at by what factor, and that factor is 2.503, and this is true for all quadratic maps. By quadratic map, I mean a map where the maximum of this maximum is the leading order is quadratic. Now, you can do this very accurately for superstable orbits. Remember that a superstable orbit is one where the derivative, this f prime, is equal to 0. If you have a periodic orbit of period k, then its stability is determined by the following multiplier. F prime k is just f prime of x1, f prime of x2 all the way up till f prime of xk, because the periodic orbit itself is x1, x2 all the way up till xk, and then repeating over again. So, this multiplier over here is just the product of the slope of the function at all the points on the period. The lowest value that this quantity can take in magnitude is 0, and this can happen when one of these points, x1 or x2 or whatever, when one of them is the map maximum. If this is some x sub j, then f prime of x sub j is equal to 0, and this entire product would vanish. This defines a superstable orbit. For the logistic map, this means that if the point half is one of the points of the cycle, then one has a superstable orbit. Clearly, for half to be the period 1 point, we must have r is equal to 2, because r x into 1 minus x. So, 2 times a half into a half gives you a half. So, half becomes a period 1 point only when r takes the value 2, and we call this r bar 0, 0 to tell you that it was period 1, 2 to the power 0, r bar to say that this is the value where you have super stability. One of the tutorials you have to work out that period 2 is super stable for the value of r1, which is 1 plus the square root of 5. And for any k, you can solve this equation, f to the k of a half is equal to half. This determines the superstability condition, but this is now a polynomial in R. It is a polynomial in the parameter. And this can be solved by Newton's method, and this is in fact what Feigenbaum did in his early calculations. And when you do this for all the powers of 2, you determine that these windows are m plus 1 minus r m divided by r m minus r m minus 1. Again, this is inverse over here. This ratio delta also has the same limiting value, that delta m goes to delta, which is 4.669. So, whether you take the points of the bifurcation or you take the points where the superstable orbits are created, the same kind of scaling operates, and you find that the ratio is 4.669. Furthermore, the elements of a superstable orbit of period 2 to the m, what are these? These, you start at a half, you map f to the half, f2 to the half, and so on, all the way up till 2 to the m to the half, which is equal to a half. Now, if you define delta m to be the distance between the point half and exactly midway along this cycle, so f to the 2m minus 1 of a half, so that is the distance between the point half and 1/2 the number of iterations on this particular cycle, this defines a quantity delta m. And in the limit delta m divided by delta m plus 1, these points also get closer and closer together. They flip from side to side, and this, as m goes to infinity, reaches the ratio of minus alpha, which is minus 2.5029, etc., which is the same quantity that we discovered in the doubling transformation. Visually, see, here is the line x is equal to a half, and when you superimpose it on the bifurcation diagram, you notice that this is the point where period 2 is superstable, that is the point where period 4 is superstable, then there is a point where period 8 is superstable, and so on. The quantity delta 1 is the difference or the distance between the superstable of this point half and its first iterate. Delta 2 is the difference between the point half and the second iterate, because this is a period 4 superstable orbit. Delta 3 is this quantity over here, and that is the difference between the point half and its fourth iterate, because it is a period 8 superstable. So, as these values are delta 1, delta 2, delta 3, and so on, as you can see that they are shrinking, and in the limit they go to the value minus alpha. These are universal constants, and their discovery has been a very important step in this entire study of nonlinear dynamics. All unimodal maps, that is, all maps with a single maximum and a quadratic maximum at the top, the period doublings are characterized by the same values of the two constants. These constants appear in other points also, but the importance over here is that regardless of what kind of map you have, the details don't matter. So, this will apply to the quadratic map. If instead of the quadratic map you study sine pi x or some map like that, that will also have the same numbers and so on. Now, the cascade of bifurcations that lead to the onset of chaos at R infinity, this requires explanation by the so-called functional renormalization group, developed again extensively in the 70s and 80s. And this helps you to understand why the function, when doubled, rescaled, flipped around, etc., looks like itself. When it's formalized, then from this you can calculate these values of both alpha and with a little more difficulty also delta. Those of you who have a copy of the Strogatz book, you'd like to see section 10.7 in that text where this is discussed in detail. And there is a very nice and sort of very perturbative argument and algebraic approach without renormalization and so on, described by Virendra Singh. There's an article in Pramana in 1985, and I would recommend that strongly for anybody who'd like to take it and perhaps even apply it beyond just quadratic maps.